Yeah, so I will talk about the Julia programming language. I will talk about, first of all, the big picture, like what is Julia and what's the motivation behind creating Julia, what's the motivation for you to use Julia. I will take a little bit of a deep dive into Julia by talking about types and how Julia's type system makes it extensible. I will talk about a few goodies of Julia, which are small things, but altogether they make using Julia much more convenient. I will talk about the Julia ecosystem and give you a few pointers about how to start and what's our experience with it. And finally, I will tell you how our company, Cursor Insight, uses Julia. Right, so the big picture. Imagine that you have a task, and your task is that you need to implement a computation, and it's important for your computation to have a high performance. What do? The first thing that you can do is to choose a statically typed language, because these languages are fast, so like C, C++, or Java. These languages are like a horse, because you have to put in some effort to explain it to go from A to B, but once you have done that, they are really fast. The problem is that you have to deal with the static type system, which requires time and effort from you. These languages usually don't have syntax for math and don't have a way to extend the language itself. So again, you have to type more and build a larger software to do the same thing. In addition, in some languages you have even additional work. So for example, in C you have to deal with memory management. In Java you have to write a lot of boilerplate code. Your other choice is to pick a dynamically typed language. So for example, you can pick Python or MATLAB or R. These languages are good because you can be very productive with them. You don't really have to think about the type system, which would get into a way. But the problem is that they are not very efficient. And the way to solve this problem is that you have some part of the computation, which is the critical part, and you have it written in C. This is what you get with Python and NumPy. For example, NumPy provides very fast, NumPy provides very big speed. But it does that in a C core, and on the top of that you will have a convenient Python layer. So it's like putting a person on a horse. Like you can talk to a person easily, like you can talk to Python or MATLAB, and you can tell it what to do. But you have to put a horse under the man so that it will go efficiently from A to B. And the problem is that if you want to implement your own fast computation, then you have to get into C coding, and then we are back in the previous slide. And that's where Julia enters the picture. If these languages are like horses and men on horses, then what's Julia? Julia is a centaur, because it's one organism, but you can talk to it, it will understand what you want to do, and then it can do what you want really fast. It has dynamic typing. When you're programming it a bit, it feels like programming Python, but when you execute it, it feels like C. How does Julia achieve this? It's not a big surprise, I think. Java was notorious for being slow in the 20th century, but now it's almost as fast as C. What made the difference? Implementing a just-in-time compiler. What made Lua almost as fast as C? Just-in-time compiler. What made JavaScript fast? Just-in-time compiler. So what makes Julia fast? A just-in-time compiler. What makes Julia productive? One of the reasons Julia is productive is that it's very extensible. You can extend the syntax of Julia with list-like macros, and you can utilize Julia's type system, and the magic expression here is multiple dispatch, and I will explain what this multiple dispatch means. it's a way for you to extend the type system in a way that's much stronger in most languages, and still fast. And finally, Julia was designed with math in mind, which contributes to both being fast and both being productive. So now let's look into this multiple dispatch and what I mean by multiple dispatch making the type system more extensible. First, of course, I will have to show you a hello world. This is pretty simple in Julia. You just say println hello world. You put it into a Julia file, and then you execute it from a shell. Here you can see that in Julia you don't need to use modules, you don't need to put your code into functions, you can just put your code into a Julia file, and whenever you tell Julia to execute it, it will just simply read your file and execute it. So that's why I mean like it feels like Python. Type declarations. You can write a hello world like this. Here we have a hello function which has a string parameter. But you didn't say to Julia that this is a string parameter. This will work just fine, but if you want to add a type declaration, you can do that. You can tell Julia that the first parameter of this function can only be a string. What happens when you specify a different type? Then you will get a method error, and it will tell you that you were trying to call this hello function with an integer, but actually there is only one hello function, and it only accepts strings. So one reason for writing type declarations is that you can make your functions safer and you can catch errors earlier. The other reason is making the human reader's life easier. So when I'm reading this hello function, I can know that this works with strings. The third reason is to implement multiple dispatch. At the first sight, it looks like function overloading. So here we have a hello function that accepts a string, and we have a hello function that accepts an integer. And when I'm calling hello world, then the first one will be executed, and when I'm calling hello 42, the second will be executed. But it's not function overloading, and the trick here is that this decision about which function to call, which version of this function to call, will be made at runtime. Languages like C++ and Java that have function overloading can do this kind of stuff at compilation time. That's called function overload. Or you can use a so-called subtype polymorphism. So this is when you have an object, and one descendant of the object has a hello, and the other descendant of the object will have another hello, and in runtime your running environment will decide which one to call. But that's not really general, because you can do that only for the object. So basically you can only do that for the first and implicit parameter of your method. Here you can do that anywhere, in any parameter. So if you take function overload and you take subtype polymorphism and put them together, multiple dispatch is even better than those two put together. Let's see a bit more concrete or useful example. There is a function in Julia called plus. It's the addition operator, but that's actually just a simple function, so you can add new implementations to this function with different types. So if I open the Julia shell and I type methods plus, then it will list me all the 163 methods implementations for this function that I have in my particular environment. Every new package is free to add as many implementations as it wishes. And you can even see in this example that these functions may reside in different files. The first one, which knows how to add the bool type and the complex bool type, whatever that is, resides in complex.jl, while the second one, which knows how to add two bool variables together, resides in bool.jl. So now let's see how we can add our own type to this function. In Julia, types are not very complicated in the sense that they're not like objects. In object-oriented languages, you can have methods. Here, types are mostly structs. So here I have a struct called my, which has one field, and that field is called x, and this type is a number. I want to define a plus operator, so that it will add two my structs together, and this is exactly what I do. I import base.plus, because that's the function that I want to add my new implementation to. And then I write my new implementation. It will accept two my structs called a and b. It will read the x field from both of them, add them together, and create a new my struct with the sum. And when I say my plus my 2, sorry, my 1 plus my 2, then I will get my 3 as expected. All this happens in runtime. Okay, now let's see what can we do when we want to add any number to our type. So if I have a my struct, then I want to be able to write 1 plus and my struct, or my struct plus 1. In object-oriented languages, you can usually do it only in one direction. This is how you do it in Julia. Besides multiple dispatch, you also use parametric polymorphism, which sounds like a scary word, but you already know it, because if you think of templates in C++ or generics in Java, this is the same thing but with a fancier name. So that means that when I define a new function, like the first one, instead of specifying concrete types for all of my parameters, some of the parameters will have a type about which I'm just stating something. So here I have a my struct in A, and in B I'm just stating that this B has to have a T type, and T must be a type which belongs to type number. So that means that if I'm passing a float, if I'm passing an integer, then this implementation can be selected by Julia at runtime. If I'm passing something that's not a number, then it won't be selected. The second function is basically the same, just in a different order. And the last line shows you how it works. If you add 1 plus a struct, then you will get a new struct. Okay, so this was the hard part of the presentation. Now let's get into the easy part, the goodies. Julia has a quite modern design, at least in my opinion, and by that I mean that there are many language features that the language designers or the language designing community realize that they are probably good things in new languages, or even if not, they are cool and trendy things. So there will be a bunch of things like that in this slide. I'm just going through them. So Julia has a garbage collector. You can have optional parameters for functions. You can have keyword parameters for functions. You can have anonymous functions, also known as lambdas. Strings are Unicode. No need to deal with Latin one and things like that. You can have multi-line strings. You have modern data structures like dictionaries. You have byte arrays, which is nice because in older languages you often have one string-like byte, and even if you have a Unicode set of characters, sequence of characters, you put that into the string type. But if you have bytes, you also put it into the string type, and then you can mess up things quite easily. So in Julia, if you have a sequence of bytes, you put them into byte arrays. If you have a sequence of characters, you put them into a string. Julia supports parallel computing. It has libraries for logging unit tests and all the trendy and cool things. You can write doc strings in Julia, and it will automatically generate HTML code for you. You can use Markdown with the doc strings. You have a Julia shell, which is very colorful and has a bunch of features. For example, inside the shell, if you hit the question mark, then you will be able to type the name of any function, and it will give you the docstring for that function. And Julia has a package manager as well, with all the dependency handling and things like that. Okay, so let's see some Julia code again. The word from which Julia is coming is the word of programming languages written for mathematical computations like R and MATLAB. So of course it has to have some support for arrays. And this is how this looks like in Julia. I can write one-dimensional arrays like 1, 2, 3, and this is how it looks like. I can write a two-dimensional array, also known as a matrix, with rows 1, 2, 3, and the other row 4, 5, 6, and this is how it looks like. If you read the type description carefully, then you will see that it is a second parameter, so like array int 64 and 1, or array int 64 and 2. And it's not a coincidence that that second number is a positive integer. You can specify any positive integers there, so you can have not only vectors and matrices, one and two dimensional arrays, but any dimensional arrays. If you work a lot with arrays, then it's convenient to use that pairwise operation on them, and that's what Julia gives you with the dot syntax. So for example, if you have a 1, 2, 3 vector and another 1, 2, 3 vector, and you use the dot plus operation, then you will get a pairwise addition. And note that this is not a special operator. This dot plus thing. In Julia, you can use this dot notation for anything. If you write a function which works with anything, then you can put a dot after it, like this one. There is a mux function, and this mux function knows nothing about vectors, but still, if you put a dot after it, then from now on it will work with arrays of any dimensions. So here I have two matrices, and I do a pairwise maximum search, and then in the result, each element will be the maximum of the appropriate corresponding element in the originator, in the source matrices. And a bunch of other little convenient things that make your site better. When you want to write 3x, like mathematicians do, you can. You don't have to write 3 times x. This underscore notation doesn't do anything, but it's accepted in Julia, and it makes your integer literals easier to read. You can write A is smaller than B, and B is smaller than C with this mathematical syntax. You can select a slice from an array. You can use the end keyword for indexing from the end of the array. So this is at the last element, but the element before the last element, and -1. Julia can calculate with infinity. So 1/0 is infinity, and 1/infinity is 0. If you expect 1/0 to be some exception, like we did initially, then you can get into trouble. There is a very nice, nice function called rationalize. Cool is a better word. It's a cool function because what it does is that you can provide a float to it, like pi in this case, and a type like integer on 16 bytes, and then it will give you a rational number whose numerator and denominator are within the specified range, so both are at most 16-bit integers, and this is the rational number from the possible rational numbers that's closest to the pi number. You have this pipe syntax for functions, so if I have an x parameter, I can push it into g, So G will be called, the G function will be called with X, and then the result will be pushed into F, so F will be called with the output of G. You can also use function composition, F circle G, and that's basically the same thing. Ecosystem. When we started using Julia, like almost 2 years ago, it was about 0.5, and then 0.6 came out, and then 0.7 came out, and then 1.0 came out, and in almost all of the releases they changed things that needed us to modify our code base. So that was one of the releases where the keyword for types was renamed. So what you have seen, struct, was called type before this. So the creators of Julia decided that it was enough time for experimentation, it's time to settle down. So in August, Julia 1.0 came out, and the goal is that this will be fixed for at least 5 years. So I mean, new things will be added, of course, but the code that you are writing now in Julia 1.0 will be running in Julia 5 years from now. Because of these changes, it's not always obvious whether a package that's written in Julia can actually be used by you, because maybe it was written a long time ago with an older Julia version. But fortunately, more and more packages are moving to 1.0. And this is also something with which we had first-hand experience. So when we started using Julia 0.5, we found a library that we wanted to use, which was written for Julia 0.3. So the first thing that we did is to migrate it to 0.5, and then to 0.6, and then to 0.7, and then to 1.0. So I encourage everyone to do this. Like if there is a library that you want to use, usually it's not a lot of work to update, you just have to replace the keywords and things like that. Okay, so if you want to use Julia, what tools do you have? There is an IDE called Juno, which seems to be the IDE that provides the most support for Julia development. I myself am a Vim person, so I haven't actually tried it, but if you're an IDE person, then this is something that you could look at. There is a tool called the Jupyter Notebooks, which is quite impressive. It's like a website, and you can write snippets of Julia code, and you can also write text in it, and it will evaluate the Julia code that you are writing. Avik will use Jupyter Notebook in his presentation, so I don't need to talk more about it. Packages, a few pointers here. There are many packages written for other languages that have bindings for Julia. So whatever you are looking for example, visualization, then it's typical that you find packages which were, for example, implemented for Python, and then have Julia wrapper around them. And you also find packages that were written natively in Julia. This is the case with visualization. So plot is the library that was written entirely in Julia, while pyplot, probably you can guess the programming language for which it was developed, is Python. This was made by plot, this image. It's similar with machine learning. Flux and KNet, these are machine learning libraries written for Julia, while OpenAI Gym is a machine learning library for Python with Julia wrapper. If you want to tinker with these libraries, you often want to have a data set that you can feed into these tools so that you can try out the computations. And fortunately, there is such a data set written for Julia. It's called market data. So finally, how do we, as Cursor Insight, the company, use Julia? First of all, we are. It's a company based in Budapest, London, and Cardiff. Most people are in Budapest, so if you are interested, get in touch. We have a motion analyzing algorithm, which is very useful for classifying motions. You can classify any kind of motions, like you can observe how people are moving, and you can try to tell whether they have a certain disease or they are not having that disease. But we are using it most these days is signature verification. So there are devices like this one on the screen that look like a tablet, but they are actually not tablets, but signature pads, where you can read a text. For example, if you go into a bank, then you can read your contract on this device, and at the end you have to sign your name on this device instead of paper. And what we do is that instead of just looking at the image of the signature, like the bank teller would do when trying to decide whether it's your signature or not, we are looking at the motion of your signature and try to tell whether it's your signature or not. This is the very basic architecture of our system. On the bottom you have the Julia code, which does the math, and on top you have our Erlang code, which is doing most other things. So as you can tell, we like languages that are not necessarily popular, but we deem them to be good for the job that we want to use them for. Erlang is running in the Erlang virtual machine, Julia is running in the Julia environment, and we had to find a way to connect these together. So we created a library called Julia port. Erlang has C bindings, Julia has C bindings, so it was an obvious choice to make Erlang and Julia communicate using C. And that's what this Julia port does. Our Erlang code, when it wants to talk to Julia, the parameters that it wants to pass are converted into serialized versions of the Erlang data structures, and this serialized data structure, which is now only a binary, a byte string or byte array, it's sent down to Julia port's Erlang component, which sends it to Julia port C component, which sends it to a library called lport. And this library is needed because this library is written in Julia, but it understands Erlang terms, so it deserializes the Erlang term and converts it into a Julia object. So our Julia code will receive Julia dictionaries and strings and arrays. Two components of this architecture are general and have nothing to do with our business, so they can be open sourced. The first one is lport, and actually this is the library that I was talking about, that we found it on GitHub, and it was using Julia 0.3. So we didn't do the initial development, but in the last 1.5 years we were pushing all the improvements and contributions to it, so that it keeps up with Julia. And we also added a bunch of other features that we needed. And you can find the original version at the first link, and you can find our improved version at the last link. Our improvements haven't been merged yet, so that's why I'm giving you both links. Julia port was made entirely by us, and it will be available at that GitHub address at the latest next Monday. And the reason is that at Monday we will have another meetup, not a Julia meetup, but an Erlang meetup with the Julia crossover, because the title of my talk will be how we made Erlang talk to Julia via C. So basically I will show you what we made with the Julia port and how you can make two languages communicate with each other that both have a common language that they understand. So to sum up, I have described you why Julia is like a centaur, because you can talk to it, but it's fast. I have shown you the magics of multiple dispatch, which is better than function overloads and subtype polymorphism together. I have shown you a bunch of Julia goodies. I gave a few pointers about the ecosystem with our experiences, and I have shown you how we are using Julia. And by the way we use Julia is not very typical. Most people use Julia for modeling, so not in the production environment, but running it in their own cluster to do computations that they can evaluate afterwards. Thank you for your attention. And there is a link for the Monday meetup if anyone